December 7th, 1941. 7:55 a.m. Pearl Harbor, Hawaii. A wall of fire erupts from the USS Arizona. The explosion is so violent it vaporizes steel. 1,177 men die in a single second. Not wounded, not missing. Gone. Erased. The shock wave rolls across the harbor, flipping sailors off their feet, shattering glass across Ford Island, and sending a column of black smoke 300 feet into the Hawaiian sky. In 20 minutes, Japan destroys what America spent 20 years building. But here is the part nobody talks about. The part that was buried in classified files for decades. Within 72 hours of the worst naval catastrophe in American history, a group of ordinary men welders, dockyard workers, a civilian bridge engineer walk into the smoke, the burning oil, and the floating wreckage. And they begin doing something the Japanese High Command declares impossible. Don't forget to like, subscribe, and turn on notifications so you never miss our next video. Join us as we uncover more incredible stories, historic events, and inspiring moments from the past. Because history is never just dates and names. It's people. It's decisions. It's the moments that changed everything. The Japanese admiral who planned this attack calculated it would keep America out of the Pacific War for at least 2 years. He was wrong. Not by a little, by everything. Because 32 months after Pearl Harbor, every single one of those sunken battleships, except 2, would be back at sea, guns loaded, hunting Japanese ships. The men who made that happen were not admirals. They were not war heroes. One of them fixed bridges for a living. His name was almost never written down. And what he did was considered by multiple Navy officers to be completely insane. This is part 1 of engineering heroes who turned Pearl Harbor disaster into triumph. The morning after the attack, the numbers are staggering. 5 battleships on the bottom of Pearl Harbor. 3 more crippled. 18 warships total damaged or destroyed. 2,403 Americans dead. The Pacific Fleet, the most powerful naval force the United States had ever assembled, is gone. Or so the world believes. Admiral Chester Nimitz, commander of the Pacific Fleet, arrives at Pearl Harbor on Christmas Day, 1941. He walks the docks. He sees the USS Oklahoma capsized her propellers, pointing at the sky like a dying animal's legs. He sees the Arizona still smoking a twisted grave for over 1,000 men. He sees the Nevada beached and burned listing in the shallows. Nimitz is a man who does not show emotion easily. But when he surveys the harbor, he says only 4 words. This is terrible. Terrible. His assessment: Nevada cannot be saved. California cannot be saved. West Virginia cannot be saved. The math is against them. The damage is too catastrophic. The Navy's priority should be the carriers, the submarines, the destroyers. Let the battleships go. Write them off. Move forward. That is the official position of the United States Navy in December 1941. Abandon the battleships. Accept the loss. Move on. But there is a man in a small wooden shack near the Pearl Harbor waterfront who does not accept that position. Commander James Steele is given command of the Pearl Harbor Salvage Division on December 14th, 1 week after the attack. His headquarters is a shack. His budget is whatever he can argue for. His workforce is a collection of Navy divers, naval yard machinists, and civilian contractors. And his mission is to do what the Navy's own admirals believe cannot be done. Steele immediately recruits the Pacific Bridge Company. These are men who build concrete structures underwater. Bridge foundations, dock pilings, underwater foundations in currents in darkness, in conditions that would kill an unprepared man. They are not sailors. They are engineers and laborers who spend their careers doing jobs that everyone else considers impossible by definition. Their lead engineer walks into that shack and looks at the aerial photographs of Pearl Harbor, the burned ships, the capsized hulls, the debris field across Battleship Row. He does not say it cannot be done. He picks up a pencil and starts drawing. What he proposes is immediately rejected by 3 separate Navy officers. The problem with raising a sunken battleship is not simply pumping out water. A battleship like the USS Nevada displaces 27,500 tons. She is 583 feet long. Her hull, in multiple locations, has been torn open by Japanese bombs and torpedo strikes. The damage to Nevada's bow alone, from a near miss that buckled and cracked. The hull plating creates a gap nearly 40 feet long and 10 feet tall in places. You cannot simply plug that hole. You cannot weld it shut underwater in the dark. You cannot do it fast enough or strong enough to hold against the pressure when the pumps engage. The Navy's proposed solution abandoned the attempt, or at minimum wait for specialized equipment from the mainland. Months away, maybe longer. The Pacific Bridge engineers' solution built a wooden wall, not a metaphorical wall, a literal wall. 4-inch thick wooden planks bolted to the outside of the battleship's hull, curved at the bottom to match the ship's profile extending above the waterline, sealed with canvas sacks, stuffed with oakum hemp fiber, soaked in pitch, and pressed into the gaps like a gasket. The whole structure braced from the inside by timber beams, held against the hull by the weight of the water itself. 3 Navy officers hear this plan and laugh. One uses the word ridiculous. Another says it is the kind of idea a man gets when he has never actually been to sea. A wooden patch on a 27,500-ton warship that has been sitting on the harbor floor for weeks. In salt water, under pressure. Preposterous. The engineer does not argue. He asks for permission to try it on the smallest, least critical wreck first. He gets it. Reluctantly. The divers go in. What they find inside those sunken ships is something no training prepares a man for. The harbor water is black with oil. Visibility is zero. The divers navigate by memory and by touch, running their hands along hull plating that is razor sharp where the explosions tore it apart. The interior corridors are flooded completely dark and filled with a sludge that is 1 part oil, 1 part harbor, mud, 1 part decomposed food from the galleys, 1 part things that were once men. Hydrogen sulfide gas produced by decomposing organic matter collects in pockets inside the hull. It is colorless. It is odorless in low concentrations. And it kills without warning. On February 7, 1942, Lieutenant James Clarkson enters the steering engine room of the Nevada during salvage operations. He does not come back out on his own. The machinist's mate who rushes in to pull him out collapses as well. The machinist dies in hospital. After that, the salvage division tests every compartment before any man enters. But they do not stop. They never stop. The wooden patches go on the Nevada first. Bolted to a hull that has been underwater for 60 days in the dark by men in heavy brass diving helmets connected to surface air pumps by rubber hoses that can be severed on any sharp edge. The canvas oakum sacks are pressed into the gaps. The interior bracing is installed 1 timber at a time, dragged through flooded corridors by men who cannot see their own hands. On February 12, 1942, 67 days after Japan's attack, the pumps engage on the USS Nevada. The water begins to drop inside the hull. Compartment by compartment, section by section. The wooden patches hold. The oakum seals hold. The interior bracing holds. At 12:30 in the afternoon, the USS Nevada, the ship that Chester Nimitz declared unsalvageable, breaks the surface of Pearl Harbor. The men on the docks stop working. Somewhere, someone starts clapping. It spreads. Within 30 seconds, every man within sight of that rising hull is making noise, fists in the air, voices raw. Nimitz watches from the dock. He says nothing for a long moment. Then, I am very glad to have been wrong. They tow Nevada to dry dock number 2. The dry dock that was just completed weeks earlier rushed to readiness specifically for this moment. When the water pumps out and her full hull is exposed for the first time since December, the damage is more severe than any external survey suggested. The wooden patches that the Navy officers called ridiculous are holding against a hull that looks like it was chewed apart from the inside. The engineer from Pacific Bridge Company looks at his work and says they will need bigger patches for the next one, because California is next, and California sank in 40 feet of water, And California's hull damage is not one torpedo hole. It is 2 torpedo strikes, multiple near-miss bomb concussions that buckled entire hull sections, a direct bomb hit that killed 50 men and set off an ammunition magazine, and 4 months of sitting in the dark harbor floor while oil and decomposing matter turned her interior into something that would not be described in polite company. The wooden patch system, the idea 3 Navy officers called preposterous, is about to be scaled up to a size that has never been attempted in the history of naval engineering. But there is a problem that nobody has solved yet. A problem that is about to blow an entire patch clean off a battleship at the worst possible moment. And when it happens, every man on that dock will have about 4 minutes to decide whether the USS California lives or goes back to the bottom forever. In Part 2, we go inside the salvage of California and West Virginia, the 2 ships that even the salvage team believed might be beyond saving. And we meet the men who went into the flooded dark armed with nothing but timber canvas and the refusal to quit. Nevada is floating again. The wooden patch idea that 3 Navy officers called ridiculous just raised a 27,500-ton battleship from the harbor floor. But California is next. And California sank in 40 feet of water with damage that makes Nevada look like a fender bender. Here is the number nobody wants to say out loud. California has a gash in her hull 40 feet long and 10 feet tall. The wooden patch system that worked on Nevada was built for a hole a fraction of that size. Scaling it up is not an engineering challenge. It is, according to Captain Raymond Thompson, the senior naval yard officer at Pearl Harbor, a fantasy. You want to bolt timber to the side of a battleship? Thompson says in the planning meeting, not as a question. Timber, in 40 feet of salt water, against a hole the size of a house. The Pacific Bridge engineer does not flinch. We want to bolt timber sections together and lower them in segments. The water pressure holds them against the hull. Same principle as Nevada, larger execution. Thompson leans back. Nevada had 1 torpedo hole. California has 2 torpedo strikes, multiple bomb concussions, and a direct hit that detonated her own ammunition magazine from the inside. You are describing a solution to a problem that is 3 times more severe using a method that barely worked once. It worked completely, the engineer says. Not barely. Thompson ends the meeting. The California project is placed under review. Review means delay. Delay means the harbor remains blocked. Delay means the men inside California's hull, the ones who have not been recovered yet, stay there longer. The salvage team does not wait for the review to conclude. They cannot, because Thompson does not know what the divers already know. They have been inside California. They have crawled through her flooded corridors in zero visibility, feeling their way past blown-apart bulkheads, past galley compartments where 4 months of submerged food has turned into a biological hazard, past compartments where the bodies of their crewmates are still present and unrecoverable without first making the ship watertight. The divers know California can be raised. They also know that without the cofferdam patches, the scaled-up wooden wall system, it cannot happen. So the Pacific Bridge team begins building the patches without formal authorization. They work at the cold dock away from Thompson's line of sight, cutting and curving 4-inch timber planks, fabricating the angle iron frames, calculating the load distribution for a structure that will span sections of hull that no salvage patch in history has covered. The ally who saves the project is not an admiral. He is a General Electric field representative named Walter Probst, sent to Pearl Harbor to assess the damage to California's turbo-electric motors. Probst walks the dry areas of the ship, takes measurements, writes his report. Then he walks over to the Pacific Bridge shack and asks to see the cofferdam drawings. He studies them for 20 minutes without speaking. Then, these will work. The load distribution is correct. The timber grade is sufficient. The oakum ceiling is standard in underwater concrete forming. I have used this principle on dam construction in Oregon. Can you put that in writing? The engineer asks. I already am, Probst says. Probst's written endorsement, combined with the fact that General Electric is simultaneously confirming California's motors can be rewound and restored, meaning the ship has real value if raised, forces the review to conclude. Thompson approves the cofferdam project on one condition: a formal demonstration, one chance. If the first major patch section floods on installation, the project is canceled and California is written off for scrap. March 15, 1942. The demonstration begins at 0600. The harbor is flat and cold. Pearl Harbor in early morning carries a particular quality of light pale, almost silver, and the smoke that hung over Battleship Row for weeks is finally gone. What remains is the silhouette of California's superstructure rising from the water. Her charred and bent upper works visible above the surface, the harbor level reaching all the way to her main deck. Thompson stands on the dock. Two other senior officers stand beside him. The Pacific Bridge crew has been working since 0400. The first cofferdam section, 13.5 feet wide, curved to match California's hull profile, weighted with lead to counteract the timber's natural buoyancy, is lifted by floating crane and moved into position over the forward torpedo damage. The divers go in first. 4 men in heavy brass helmet suits connected to surface air pumps by rubber hoses. Their job is to guide the section down, hold it against the hull as the lead weights take it to depth, and signal when it is seated correctly. Communication is by rope pull signals. 1 pull section is moving. 2 pull section is in contact with hull. 3 pulls seated and ready for bolting. The crane lowers. The section disappears below the surface. On the dock, nobody speaks. 40 seconds. 60. 90. 1 pull. The section is moving. Thompson checks his watch. One of the officers beside him says something quiet that is not meant to be heard. The Pacific Bridge engineer stands with his hands at his sides and watches the water. 2 pulls. Contact with hull. The crane operator holds tension. The divers below are now working with their hands across the face of the section, checking the seat, checking the gap between the timber and the steel. The oakum sacks, canvas tubes stuffed with pitch-soaked hemp fiber, each one packed by hand in the days before this test, are being pressed into the gap by the divers manually in the dark at depth. 3 pulls. Seated. The bolting crew goes to work. Topside men feed the bolts down through pre-drilled holes in the timber. Below, divers on the interior side of California's hull inside the ship in flooded corridors carrying tools they cannot see, locate the bolt threads by touch and apply the nuts. Each nut requires a diver to brace himself inside a flooded compartment, feel for the thread, engage the nut, and turn it without dropping it into the silt below. 11 bolts. 40 minutes. When the last signal comes up, the Pacific Bridge engineer walks to the pump station. The pump for the forward compartment, the one sealed by the new cofferdam section, engages. The water gauge drops. Slowly. Then faster. The cofferdam is holding. The oakum seal is holding. The bolts are holding. The water inside the forward section of USS California is going down. Thompson says nothing for a long time. He watches the gauge. He watches the engineer. He watches the harbor where the crane is already moving to pick up the second cofferdam section. After 12 minutes, he speaks. "How many sections total?" 16 for the main damage area, the engineer says, plus the bow cofferdam for the near-miss rupture. How long? 3 weeks for installation. Then pump-out begins. Thompson looks at the water gauge one more time. The number is still dropping. Then he turns and walks back toward the naval yard without another word. But before he rounds the corner, he stops, does not turn around. "Build them all," he says. "Every section. Don't stop." The patches go on, section by section, across California's midsection divers, installing timber and oakum in the dark, while the surface crews work the cranes and the bolt lines. The work continues through March and into early April. By the 3rd week, 14 of 16 main sections are in place. The forward bow cofferdam is complete. The interior bracing timber beams, dragged through flooded corridors and bolted against the inside face of each patch to resist the outward pressure when pumping begins, is 90% done. On March 21st, the main pumps engage. California begins to rise. She rises for 3 days. The list that develops 20 degrees at its worst, caused by the uneven harbor floor beneath her, forces the pump teams to work, compartment by compartment, in a precise sequence, or the ship will tip. Sleep becomes secondary. The pump operators work in shifts. The engineers do not leave the dock. On April 5th, California is floating. Not in dry dock, not repaired, but floating. The harbor is in her hull. The pumps are still running, but she is up. And then at 1:15 in the afternoon, the bow patch blows out. The explosion is not massive. It is not a bomb. It is the accumulated gas pressure of 4 months of decomposing organic matter. Food, paper, oil, vapor, finding an ignition source inside a sealed compartment and releasing with enough force to blow a 14-foot timber section clear of the hull. Thousands of tons of seawater flood back into the forward spaces in seconds. California's bow drops. The ship lurches. Every man on the dock runs. 2 pump crews engage emergency lines within 90 seconds. Watertight hatches slam throughout the ship. The engineer is already at the cofferdam storage frame on the floating crane, calling for a replacement section to be rigged. They hold her. By 4 minutes. California stays afloat by 4 minutes of fast decisions, and men who have been living on this dock long enough to move without thinking. She makes it into dry dock number 2 on April 9, 1942. Barely. The 2 pumps bolted to her deck are still running as the dock gates close behind her. Inside that dry dock, the real work begins. California's interior is stripped to bare metal. Miles of copper wire are re-spooled by General Electric teams in what they will later describe as the largest field motor rewind ever performed. The hull plates are heated, rolled back into shape, and rewelded. The superstructure damage is patched. The basket masts come down. On June 7, 1942, USS California steams out of Pearl Harbor under her own power. But the Japanese intelligence network in the Pacific has been watching Pearl Harbor for months. And when California moves, a signal goes out. Because Japan's naval planners have just realized something that changes their entire assessment of the Pacific War. The ships they sank are coming back. And the men who raised them have now perfected a method that can be applied to something much larger. Something that will require not 16 cofferdam sections, but an entirely different approach. Something that sits at the bottom of the harbor with its propellers pointing at the sky. In Part 3, the salvage team faces the Oklahoma. A capsized battleship. 27,500 tons completely upside down in the mud. And the only plan anyone has for raising her involves streetcar motors, steel cables, and a physics calculation that one engineer describes as theoretically sound and practically insane. Nevada raised. California raised. The wooden cofferdam system that 3 officers called ridiculous has now lifted 2 battleships from the harbor floor and sent them back to the mainland under their own power. But Japanese naval intelligence has been watching Pearl Harbor. And in Tokyo in January 1942, a report lands on the desk of Admiral Osami Nagano, Chief of the Naval General Staff. The report contains one sentence that changes Japan's entire Pacific calculation. The Americans are recovering their ships. Nagano calls an emergency meeting. The officers around the table are silent for a long time. Because the entire Pearl Harbor strategy rested on one assumption: those battleships are gone. Permanently. If they are not gone, then the operation that was supposed to cripple America for 2 years has instead bought Japan perhaps 18 months. Maybe 12. And the clock is running. Japanese submarine activity around Hawaii increases immediately. Between January and March 1942, 11 separate submarine contacts are logged within 50 miles of Pearl Harbor. 3 confirmed attempts to photograph harbor activity through periscope. The salvage crews begin working under blackout conditions after 1,800 hours. Every ship movement is classified. California's departure is not announced. When she steams out on June 7th, there are no reporters on the dock and no radio transmission. But the Oklahoma is still there, capsized, propellers in the air, and Japanese intelligence knows it because it is visible from the air, from the sea, from any approach to the harbor. The overturned hull of a 27,500-ton battleship cannot be hidden. And as long as she sits there, Tokyo believes the salvage operation has limits. There are things they calculate that even American engineering cannot reverse. They are wrong about that too. But they will not find out immediately, because in March 1942, The salvage team has a crisis that has nothing to do with the Japanese. The Oklahoma project nearly dies before it begins. Not from enemy action. From an argument. Commander Steelhead of the Salvage Division presents the writing plan to the Pearl Harbor Naval Yard Command. The concept involves 21 massive steel frames bolted to Oklahoma's exposed hull. Heavy cables run from each frame across to Ford Island. Winches on the island, powered by electric motors, salvaged from Honolulu's streetcar system, will wind the cables simultaneously, slowly rotating the capsized battleship upright. The chief of the Naval Yard, Captain John Domagal, listens to the entire presentation. Then he asks one question. What happens if she rolls too fast and the cables snap? We recalculate the winch synchronization and try again, Steele says. What happens if she rolls too fast, the cables snap, and she crushes the dry dock infrastructure on the way down? Steele does not have a clean answer for that, because there is no clean answer. If Oklahoma rolls uncontrolled, the wave action alone could damage ships in adjacent berths. The cable snap load calculated at peak tension could take out sections of the Ford Island retaining wall. The risk is real, and it is large. Domagal suspends the project for 3 weeks pending a full engineering review. 3 weeks during which the salvage team watches Oklahoma's propellers and does nothing. The review comes back with one modification. Crushed coral, thousands of tons of it must be packed under Oklahoma's bow before any righting attempt begins, giving the hull something to roll against and slowing the rotation mechanically. The modification adds 2 months of preparation. Steele accepts it. He has no choice. Then, on March 8, 1943, 15 months after the attack, the winches engage. The harbor is quiet that morning. It is 700, and the light is flat and gray. 21 cables run from Oklahoma's hull across the water to Ford Island, each one tensioned to within engineering tolerance by crews who have been calibrating the winch loads since 0400. The Pacific Bridge supervisor walks the line of winches one final time, checking each motor connection. The Honolulu streetcar motors, 32 of them, stripped from their cars and rewired for this single purpose, sit in rows on the island waiting. Steele gives the order. The motors engage. The cables tighten. Nothing happens. For 11 seconds, nothing happens. The cables hum under load. The water around Oklahoma's hull churns slightly where the tension pulls against the submerged superstructure. The winch operators hold their settings. Then she moves. Not fast, not dramatically. 1 degree, then 2. The propellers, which have pointed at the sky since December 7, 1941, shift. The motion is barely visible from the dock, but the instruments show it. 2 degrees of rotation on a 27,500-ton hull that has been sitting in harbor mud for 15 months. The work continues for 3 months, not in one session. The righting operation runs from March through June 1943, pausing repeatedly to recalibrate cables, reposition the pulling angle as Oklahoma's center of gravity shifts, and twice to repair winch motors that burn out under sustained load. The coral bed under the bow does exactly what the engineering review predicted. It slows the rotation. It prevents a sudden roll. It keeps the cables from reaching snap load. By late May, Oklahoma is at 60 degrees. Her hull is no longer fully subside down. The torpedo damage that has been buried in the harbor mud since the attack is finally visible. What the divers see when they go in on May 28th silences the dock. The port side of Oklahoma's hull has 9 distinct rupture points. Not 5, not 7. 9. The Japanese torpedo count from the attack was estimated at 5 to 7. The actual damage is 9 confirmed strikes, several of them overlapping, 2 of them hitting within feet of each other and creating a combined rupture that removed an entire section of hull plating roughly the size of a house wall. There is nothing to patch there. There is simply no hull left. The salvage team does not try to patch it. They pump air into undamaged compartments, strap steel pontoons to the hull for additional buoyancy, and on June 28, 1943, Oklahoma is upright. 667 days after she capsized. The dock crews watch her come up. Some of them have been working this harbor since December 1941. They have raised Nevada and California. They have watched Shaw steam out with a temporary bow. They have sent West Virginia to dry dock. But Oklahoma is different. Oklahoma was the one that everyone, including the salvage team, privately considered impossible. When she is upright, no one cheers. The damage is too visible, too complete. The hull is open to the sky in sections. Inside, when the teams go in, they find the remains of more than 400 men, all of them gone since the morning of December 7, 1941. The recovery takes weeks. It is the hardest work any of these men have ever done. Oklahoma will not fight again. The damage is beyond what any repair program can justify, and the naval architects confirm what the divers already know. There is not enough hull left to rebuild from. She is stripped of every reusable component. Boilers, generators, gun mounts, fire control systems, cataloged and distributed to ships that need them. Her hull is patched to float, but the patches are for transit only. The Oklahoma righting operation is briefed to Admiral Nimitz on July 4, 1943. The man who stood on the dock in December 1941 and said, "This is terrible, terrible," reads the engineering report without speaking. When he finishes, he looks at the Pacific Bridge supervisor and asks how many men were involved in the righting operation from start to finish. The answer is roughly 400 workers, over 15 months. Nimitz writes a commendation that afternoon. It is classified for the duration of the war, but the righting of Oklahoma does something beyond the ship itself. It proves that the Pearl Harbor salvage operation has no ceiling. Every naval planner in the Pacific, American, and Japanese now knows that the harbor attack of December 7th has been not reversed but absorbed. The ships are back. The facility is functioning. And the men who did it have spent 18 months developing techniques that no salvage operation in history had ever attempted. Japanese strategic planning memos from mid-1943, captured after the war and declassified in 1947, show that the Oklahoma righting is specifically cited as a factor in revised Pacific War timeline estimates. The assumption that Pearl Harbor would keep the American battleship fleet neutralized through late 1944 is formally abandoned in August 1943. The Imperial Navy begins accelerating its own construction programs in response. Too late. The ships that were raised at Pearl Harbor are already at sea. But there is a name that appears in none of the commendations, none of the classified reports, none of the Navy press releases. The man who drew the first cofferdam diagram in that waterfront shack. The Pacific Bridge engineer who stood in front of Captain Thompson and said, "The wooden wall will hold," and was right. He will not receive a medal. He will not appear in the newspapers. When the war ends and the Pearl Harbor salvage story is written, his name will be a footnote in a technical appendix that almost no one reads. What happened to him after the harbor was cleared? What happened to all of them? The divers, the machinists, the men who spent 2 years breathing oil and gas and working in the dark, inside ships that were supposed to be dead. In Part 4, the final chapter. The men behind the miracle. What history forgot and why it matters. From a wooden shack at Pearl Harbor, a group of ordinary men raised battleships that admirals declared unsalvageable. Nevada up in 67 days. California floating on April 5th. Oklahoma righted after 15 months of cable, coral, and streetcar motors. Ships that Japan's naval planners counted as permanent losses were back at sea, guns loaded before the war's midpoint. But the man who drew the first cofferdam diagram never made the newspapers. And what happened to him after the harbor cleared is a story that almost nobody tells. Because success sometimes comes with a price. And in this case, the price was invisibility. The Pacific Bridge Company's lead engineer on the Pearl Harbor project finished his work at the harbor in late 1943. By that point, the salvage division had completed operations on every ship that could be raised. Nevada was at Puget Sound being modernized. California was being rebuilt with 40 new anti-aircraft guns. West Virginia was in dry dock. Oklahoma was stripped to her frames, her machinery cataloged and distributed to ships that needed it. The engineer returned to civilian work. No ceremony, no press release. His name does not appear in the Navy's official salvage history published in 1949. It appears in one technical appendix listed among Pacific Bridge Company personnel, with his role described as structural consultant. That is the full extent of his official recognition. He went back to building bridges, not because he was pushed out or overlooked by any single decision, but because the Navy's institutional machinery, the same machinery that had resisted the cofferdam idea in the first place, was not built to honor civilians. Medals went to officers. Commendations went to officers. The written record of the Pearl Harbor salvage operation was compiled by officers for officers, and the men from Pacific Bridge appear in it the way contractors appear in any government document, present in the work, absent from the credit. Captain Homer Wallen, who commanded the Salvage Division from January 1942 onward, did write one line that stands apart from the bureaucratic language surrounding it. He wrote, "Enough cannot be said in praise of the salvage crew. They worked hard and earnestly, and they soon saw that the results of their efforts exceeded the fondest hopes of their supporters." That sentence is the closest thing to a public acknowledgement that most of these men ever received. The divers fared similarly. The men who spent over 20,000 hours underwater in the oily black water of Pearl Harbor, navigating flooded corridors by touch, dragging timber through spaces too small to turn around and breathing through rubber hoses that could be cut on any sharp edge, they went home when the job was done. Some returned to commercial diving. Some went into Navy service in other theaters. At least 2 died in subsequent operations unrelated to Pearl Harbor. Their names are not on the Arizona Memorial, but their work is there, in the water, in the fact that the memorial exists at all, because Pearl Harbor functions as a naval station today, in part because of the channel they cleared and the harbor they restored. The technical legacy of the Pearl Harbor salvage operation moved faster and farther than the men who created it. The cofferdam patch system, the specific method of bolting curved timber sections to a damaged hull, sealing with oakum and canvas bracing from the interior, was formally documented by the Navy Bureau of Ships in 1943 and distributed to salvage teams in both the Pacific and Atlantic theaters. Within 18 months of California's raising, the method had been applied to 7 additional vessels in the Pacific alone, including 2 destroyers sunk at Guadalcanal and 1 cruiser damaged in the Coral Sea area. The true MIE concrete sealing method, used on West Virginia, pouring specialized underwater concrete through vertical pipes to seal the base of a massive patch structure, became standard procedure for any large-scale underwater hull repair, requiring an impermeable seal along an irregular surface. Marine salvage companies in the United States, Britain, and Australia were trained in the technique through 1944 and 1945. After the war, the method transferred directly into civilian harbor construction and offshore drilling support infrastructure. It is still in use today, modified for modern materials, but built on the same principle that the Pacific Bridge Company developed in the harbor mud of Pearl Harbor in 1942. The righting operation on Oklahoma, specifically the system of synchronized cable winches and progressive tension adjustment that allowed a 27,500-ton hull to be rotated over a period of months without structural collapse, informed every subsequent large-scale vessel righting operation for the next 4 decades. When the Swedish warship Vasa raised from Stockholm Harbor in 1961, required stabilization during its slow rotation from the bottom, the engineering team consulted the Oklahoma righting documentation. When the Italian cruise ship Costa Concordia was righted in 2013, after capsizing off the island of Giglio, the operation used computer-assisted winch synchronization that is a direct descendant of the manual synchronization developed for Oklahoma in 1943. The Costa Concordia weighed 114,000 tons. Oklahoma weighed 27,500. The principle is the same. The physics have not changed. The total accounting of what Pearl Harbor salvage produced is this: 18 warships damaged or sunk on December 7, 1941. 15 returned to service. Of those 15, 11 saw active combat operations before the war's end. The 3 that were not returned, Arizona, Utah, and Oklahoma, were either complete losses from the first morning or deemed beyond economical repair. Every other ship came back. Those 11 combat-returned ships participated in engagements, including Leyte Gulf, Suriago, Strait, Iwo Jima, Okinawa, and the Normandy bombardment in Nevada's case. Their combined gunfire expended in combat operations against Japanese forces runs into the hundreds of thousands of rounds. The cascading effect of having those hulls available, rather than having to build replacements from scratch, compressed the Pacific campaign timeline by an estimated 6 to 14 months, according to post-war Navy logistics analysis. 6 to 14 months of war. The human arithmetic of that compression is impossible to calculate with precision. But it is not nothing. The deeper lesson is not about engineering. It is about the moment before the engineering, the moment when a civilian contractor stood in front of a senior naval officer and said, "The wooden wall will hold," and the officer laughed, and the contractor built it anyway. The institutional resistance to the cofferdam idea was not stupidity. Captain Thompson was not an incompetent man. He was an experienced naval officer, applying the logic of his experience to a problem that existed outside that experience. His knowledge told him wooden patches do not hold against a flooded battleship hull. He was right about every wooden patch that had ever been tried before. He was wrong about this one, because this one was different, and the difference was not obvious from inside the institution. This pattern appears repeatedly in military history. The tank was rejected by cavalry commanders who understood horses and did not understand armor. The aircraft carrier was opposed by battleship admirals who understood gun range and did not understand air power. The atomic bomb project was considered scientifically credible but strategically marginal by several senior Army officers as late as 1944. In each case, the resistance came not from ignorance, but from expertise applied to the wrong category of problem. The Pearl Harbor salvage team succeeded because the civilians from Pacific Bridge did not carry the institutional memory that told them what was impossible. They carried bridge-building logic into a ship-raising problem and found that the principles transferred. The oakum gasket is a dam construction technique. The interior timber bracing is a tunnel shoring technique. The progressive compartment pumping is a foundation dewatering technique. None of it was invented for ships. All of it worked on ships. Now for the detail that almost no historical account includes. The one that changes how the whole story reads. The electric motors that powered the Oklahoma righting operation, the 32 motors pulled from Honolulu's streetcar system, were returned to the city after the operation was complete. They went back into the trams. The same motors that rotated a capsized battleship in Pearl Harbor spent the rest of their working lives carrying civilian passengers through downtown Honolulu. The Honolulu streetcar system was decommissioned in 1941 before the attack, and the motors had been in storage. They were borrowed for the Oklahoma job. Afterward, the Navy paid to have them overhauled and offered them back to the city. The city, facing post-war budget constraints, never reinstalled the streetcar lines. The motors were eventually scrapped in 1947, but for roughly 16 months in 1943 and early 1944, those motors did two things that no motor is ever asked to do. They raised a dead battleship from harbor mud, and they waited patient and silent to carry someone to work. There is something in that detail that resists easy summary. These were not weapons. They were not built for war. They were transit equipment, ordinary civic infrastructure, the kind of thing that exists in every city and that nobody thinks about. And for 16 months, they were the most important machines in the Pearl Harbor salvage operation. The difference between Oklahoma staying upside down and Oklahoma coming upright. From a wooden shack at Pearl Harbor's waterfront with a pencil and a set of engineering principles borrowed from bridge construction, a civilian changed the arithmetic of the Pacific War. The salvage team he worked with raised 15 ships, sent 11 of them back into combat, and developed techniques still used in marine salvage today. They did it in conditions that were described by every man who worked in them as the worst they had ever experienced, and they did it without stopping. Because the job was there and it needed doing. 3 admirals said it could not be done. The ship said otherwise. If you know a story like this one, a story of an ordinary person, and an idea that was called impossible, leave it in the comments. These are the stories that the official histories skip, and they are the ones worth keeping. Subscribe so you see the next one when it comes, because there are hundreds more where this came from every theater of the Second World War, from every branch, from men and women, whose names deserve to be spoken. The Japanese Navy launched 353 aircraft at Pearl Harbor on December 7, 1941, and expected to end American power in the Pacific. What they actually did was hand a group of bridge engineers, Navy divers, and dockyard machinists the most difficult salvage problem in maritime history. And those men solved it. Every day for 2 years they went into the dark water and the toxic air and the impossible spaces, and they worked. That is what humans do when the job needs doing. They find a way. And sometimes the way is a wooden wall bolted to the side of a battleship at the bottom of a harbor, held in place by nothing more than water pressure and the refusal to quit.